So now the decay rate, the equation for decay rate. I've got it posted on the board, but I want to talk about it really quick. Now, when we talk about decay, we're talking about we're having a huge amount of isotopes in a small area. We're talking a massive number of particles. So when we talk about radioactive decay and this half-life, it doesn't mean that you have a chunk and all of it, half of it well, it does mean that, but it's not a step. Okay, it's not like all of a sudden half-life happens. Boom, it moves down to here. Booms down to here. This is a random motion. This happens randomly. I can't say I got 4 particles and exactly 2 seconds later I have 2 particles that are the originals and 2 particles that are a different type of material. They've given up a proton, or I mean they've given up an electron, or they've given up a hydrogen particle, or not a hydrogen, a helium particle. It's undergone alpha decay or beta decay exactly 2 seconds later. It's random when these things accomplish. But if you have a huge number, a huge pool of particles, you can say, well, boom, 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 because you're talking about billions of particles. So it appears that it goes, you know, exactly 2 seconds later I have half of them here, exactly 2 seconds later half of them again, exactly 2 seconds later half of them again. But it's a random reaction, but because your pool is so large that it appears to be non-random. It appears to be this relationship that's described at this equation. Okay, but remember, the importance is that it's random, but because the numbers here, this N and NO, this NO is such a huge number of particles that this randomness appears to be regular. It appears to be consistent. I mean, it's all statistics. It's all probabilities. If you make your well big enough, if you make your probabilities, your numbers of initial systems big enough, then you can describe it by using these equations. But if it's a small number of particles, if it's only 4 particles, there's no guarantee that your 4 particles are going to be down to 2 particles in 2 seconds. But if it's huge, like Avogadro's number huge, then you're allowed to say, well, I would expect half of them will have transformed by now, and another half will transform by now, just simply by the sheer size of it. Okay, so just really quick, I wanted to make that point. It's a random reaction. That doesn't mean that it's a random reaction, and if you have a small number of particles, it doesn't necessarily follow that decay rate. But if it's a large number of particles, because of the sheer size of it, there's a high probability that half of them are going to be transformed. Okay, just to be really, really specific about that. It's not an exact process. As a matter of fact, like I said, 4 particles in 2 seconds, because let's say the decay rate is 2 seconds. In 2 seconds, you may still have all 4 particles, because your sample size is so small. Okay, but because we're usually talking about huge sample sizes, we're allowed to get away with the statistics to this equation. Okay, so really quick, what we would expect to see for this is something like this. So here's my number of particles. So this is the number of particles, and this is NO, the initial number of particles, or in some cases this can be expressed as masses, because you know masses are when we're talking about moles, we're talking about number of particles per unit of mass. I mean, they can be kind of interchangeable at that point when we talk about that mole and molarity. So here's the amount of particles, or in some cases the amount of mass we start off with, and you get something that looks like this. Okay, which means that from here, 1/2 of MO, half of the original value, is experienced somewhere along here. And then if we take this time value, this T1, and we double it again to T2, we experience half of that original value. Now, I didn't draw this very well. I mean, obviously it should look something more like this, so that the T2 is half of this. So this drop here is half of the original. This drop is half of half. So this is going to be a 1/4. Right here is going to be 1/4. 1/4, not 1/2. Gosh, my brain is not running. MO. Okay, I do it again. I experience the exact same time, T3, T1, T2, T3, all being the same size. 1 second or 1,000 years, whatever it is, and then we experience half of a fourth. Okay, continuing down the period, the size here, boom, 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 cutting it by half, by half, by half, all the way down there. That's a half-life. So in a given amount of time, which is called this half-life, okay, in the given amount of time here, this amount of mass, or the amount of particles of a particular element, has now been converted to a different element, and it continues to go down. So I lose the original elements, but I'm actually gaining the other elements. So there's another curve here that says, alright, now this is talking about one type of particle, the original one type of element. I'm losing that element, but I'm shifting to a different kind of element. Okay, and it's not exactly the same because you have other reactions that are going on. You may be ripping off for alpha, or for an alpha particle, but that alpha particle is now, leaving it unstable, so you get a transformation to a different type of particle. So it's not necessarily shifting from one element to another, but this original element is shifting away. You're losing more and more of those elements. I'm just kind of rambling at that point. So you can kind of diss that idea. Okay, but this is the original amount of the original element shifting down to a new type of element. Okay, so that's where you get this half-life. Now this T1, T2, this T1 equaling T2 equaling T3 turns out to be equaling that value here, this lambda, which is referring to the half-life. Okay, it's a specific value. So when we refer to the half-life of something radioactive, this number right here, this alpha, is how many is T? How long does it take for it to be reduced to a half, and a half again, and a half again, and a half again? Okay, so that is radioactive decay. That's the equation for radioactive decay. Cool. Now it doesn't describe which radiation process is going on. It doesn't say whether it's alpha radiation or beta radiation. You won't see this with gamma radiation, because gamma radiation, you're not changing elements, you're just reorganizing your protons and your neutrons. So this kind of alpha decay and this gamma decay is just basically this kind of equation is referring basically to beta and alpha decay. Okay, cool.